The Fermi Paradox is a contradiction between the high probability of extraterrestrial civilizations existing in the vast universe and the lack of any clear evidence or contact with such civilizations. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" During a casual lunch conversation in 1950, the paradox forces us to confront the unsettling silence of the cosmos, despite its overwhelming potential for life. The universe is around 13.8 billion years old, containing over 100 billion galaxies, each with billions of stars and potentially even more planets. Given the age and size of the universe, many of these planets should have had enough time to develop intelligent life, advance technologically, and potentially colonize the galaxy or send detectable signals. The Drake equation attempts to estimate the number of civilizations we might expect to detect, often yielding results that suggest we should see evidence of alien life frequently. Yet, no definitive signals, megastructures, or visitations have been observed, leading to a profound cosmic silence. Several hypotheses attempt to resolve this paradox. Some suggest that life is extremely rare or fragile, requiring such a precise combination of factors that Earth is a rare exception in the cosmos. Others propose that intelligent life frequently self-destructs through technological means before achieving interstellar communication or travel, a concept known as the Great Filter. It is also possible that advanced civilizations exist, but choose to remain silent, following a zoo hypothesis where they observe without contact, or they may communicate in ways we do not yet understand. Technological limitations may play a role, as our window of radio-based communication is tiny on a cosmic timescale, and signals may be too weak, transient, or outside the frequencies we monitor. Furthermore, the immense distances between stars make direct travel or communication challenging, and any messages may take thousands or millions of years to arrive. The Fermi Paradox remains significant because it forces humanity to examine its place in the universe, questioning the uniqueness of life on Earth and the future trajectory of our civilization. Whether it implies we are truly alone or surrounded by silent, hidden civilizations, the paradox is a reminder of both the vast potential of the universe and the limitations of our current understanding. Olbers Paradox questions a simple but profound observation. If the universe is infinite and filled with stars, why is the night sky dark instead of bright? First formally stated by German astronomer Heinrich Wilhelm Olbers in 1823, this paradox challenges our understanding of the cosmos using logic that seems impossible to refute. If stars are scattered uniformly across an infinite, eternal universe, then every line of sight should end with the surface of a star, making the entire night sky as bright as the surface of the sun. Yet when we look up at night, the sky is mostly black, dotted only with points of starlight. The paradox rests on several assumptions: that the universe is static, infinite, and eternal, that stars are distributed uniformly, and that the laws of physics have remained consistent throughout time. Under these conditions, the brightness from distant stars should accumulate and light up the night sky completely. However, the darkness we observe suggests that one or more of these assumptions must be incorrect. The resolution to Olbers' paradox emerged with the development of modern cosmology, particularly with Edgar Allan Poe's insight in 1848, later supported by the Big Bang theory and the concept of an expanding universe. The universe has a finite age, approximately 13.8 billion years, which means that we can only see the light from objects whose light has had time to reach us. There hasn't been enough time for light from all regions of the universe to arrive, leaving vast areas of darkness. Additionally, as the universe expands, the light from distant galaxies is redshifted, stretching into infrared and microwave wavelengths, rendering it invisible to the naked eye. Moreover, stars themselves have finite lifespans, and there are vast stretches of empty space between them, further reducing the cumulative light that reaches Earth. The cosmic microwave background radiation, a faint glow left over from the early universe, represents the cooled remnant of this cosmic light, visible only with special instruments not to the human eye. Olbers' paradox, once a profound mystery, now highlights the dynamic and evolving nature of the cosmos, emphasizing that the darkness of the night sky is evidence of a universe that is expanding, finite in age, and filled with cosmic history we continue to uncover. The black hole information paradox is one of the most puzzling conflicts in modern physics, challenging the foundations of quantum mechanics and general relativity. At its core, it questions whether information that falls into a black hole is lost forever, violating the fundamental principle in quantum mechanics that information cannot be destroyed. Black holes are regions in space with gravitational pulls so intense that nothing, not even light, can escape once past the event horizon. In 1974, Stephen Hawking discovered that black holes are not entirely black. They emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This radiation causes black holes to lose mass and eventually evaporate over immense timescales. The paradox arises because Hawking radiation appears to be thermal and random, carrying no information about the matter that originally fell into the black hole. If the black hole completely evaporates, the information about its content seems to vanish, directly violating quantum determinism. This paradox creates a profound tension. General relativity predicts the loss of information within a singularity, while quantum mechanics insists on information conservation. This conflict suggests that either quantum mechanics or general relativity, or both, require modification to resolve the paradox. Over the decades, several theories have been proposed to address the paradox. One idea suggests that information is somehow encoded within the Hawking radiation, though how this would work remains unclear. Another approach involves the holographic principle, which suggests that all the information contained within a volume of space can be described by information encoded on its boundary, implying that information falling into a black hole could be stored at its event horizon. Additionally, the firewall hypothesis posits that a wall of high-energy particles at the event horizon could destroy any information attempting to enter, but this contradicts the equivalence principle of general relativity. Recent progress, including Hawking's later proposals, indicates that subtle quantum correlations in Hawking radiation may indeed preserve information, though a complete resolution requires a full theory of quantum gravity, which remains one of physics' greatest challenges. The black hole information paradox forces us to confront the deepest questions about the nature of reality, space, time, and information, suggesting that unlocking its secrets may lead to a unified theory that can fully describe the universe. The twin paradox is a famous thought experiment in Einstein's theory of special relativity that explores the counterintuitive nature of time when dealing with high-speed travel close to the speed of light. It involves identical twins. One remains on Earth, while the other embarks on a journey into space at near light speed before returning. According to the theory of time dilation and special relativity, the traveling twin should age more slowly than the twin who remains on Earth. This leads to the paradox. Each twin sees the other's clock as ticking more slowly, so how can one be younger upon reunion? The key to resolving the paradox lies in recognizing that the situation is not symmetrical. The twin on Earth remains in an inertial frame of reference, experiencing no acceleration, while the traveling twin changes frames when turning around to return to Earth, undergoing acceleration and deceleration. Special relativity predicts that during the high-speed portions of the journey, the traveling twin's clock will tick more slowly relative to the Earth twin's clock, and the period of acceleration further contributes to the asymmetry. For example, if the traveling twin flies to a star system 10 light-years away at 99% the speed of light and returns, decades may pass on Earth while only a few years pass for the traveler. Upon reunion, the spacefaring twin is significantly younger than their sibling. This phenomenon has been experimentally confirmed on a smaller scale using atomic clocks flown on jets or satellites, which have shown measurable time differences compared to stationary clocks on Earth. The twin paradox highlights the reality of time dilation and demonstrates that time is not absolute but relative, depending on the observer's motion. It challenges our intuitive understanding of time and aging, illustrating that high-speed space travel would effectively allow a traveler to move into the future relative to those who remain behind. Beyond being a thought experiment, the paradox has practical implications in GPS technology, where relativistic effects must be accounted for to maintain accurate positioning data. The twin paradox continues to capture the imagination, highlighting the bizarre yet real consequences of Einstein's theories, and serving as a window into the possibilities of time manipulation and interstellar travel, where a journey to distant stars could result in the traveler experiencing much less time than those remaining on Earth. The heat-death paradox is a deep question in cosmology and thermodynamics that asks, if the universe has existed for an infinite time, why hasn't it already reached a state of maximum entropy known as heat death? According to the second law of thermodynamics, entropy, or the measure of disorder in a system, always increases in a closed system. Over enough time, energy becomes evenly distributed and no work can be extracted from it, leading to a state of thermal equilibrium where no processes can occur, a heat death. If the universe were infinitely old, logic suggests it should already be in this state, devoid of stars, galaxies, and life, existing only as a cold, dark expanse of evenly distributed particles. However, the universe around us is dynamic and structured, filled with stars, galaxies, and complex systems, implying that it is far from thermal equilibrium. This contradiction between thermodynamic law and cosmic observation forms the heat-death paradox. The resolution to this paradox came with the discovery that the universe is not eternal in the past but has a finite age, approximately 13.8 billion years, beginning with the Big Bang. Since the universe had a low entropy beginning, there has not yet been enough time for it to reach maximum entropy. Additionally, the expansion of the universe continually increases the space in which energy and matter can spread, delaying the approach to heat death. Another aspect is that gravity creates local decreases in entropy by forming stars, galaxies, and black holes, even as the total entropy of the universe increases. This process allows for complex structures and energy gradients, enabling the existence of life and the ongoing cosmic evolution we observe today. While the paradox has been resolved by recognizing the universe's finite age and expansion, heat death remains a predicted ultimate fate of the cosmos. Given enough time, all stars will burn out, black holes will evaporate via Hawking radiation, and matter will decay, leaving a dark, cold universe where entropy is maximized and no energy differences remain to drive processes. The heat-death paradox challenges our understanding of time, entropy, and the universe's fate, reminding us that the universe's current complexity and liveliness are temporary stages in an evolving cosmic story that will eventually lead to a silent, entropic end. The Bootstrap Paradox is a fascinating and mind-bending scenario in time travel theory, where an object, piece of information, or even a person is sent back in time and becomes trapped within an infinite cause and effect loop, having no clear point of origin. It is called bootstrap because it seems as if something is pulling itself into existence from nothing, like the phrase, pulling oneself up by one's bootstraps. A classic example involves a time traveler going back to the past and giving Shakespeare a copy of his own plays. Shakespeare publishes them, and centuries later the same copy is found by the time traveler, who then takes it back in time to give to Shakespeare. The question arises, who originally wrote the plays? They exist within a closed loop, with no true creation point. This paradox challenges the concept of causality, the principle that every effect has a cause that precedes it. The Bootstrap Paradox suggests an effect can become its own cause, creating a circular timeline where the origin is undefined. It raises questions about free will, determinism, and the consistency of time travel, as the information or object exists within the loop without being created in the traditional sense. The paradox is commonly explored in science fiction, such as in the television series Doctor Who, where a time traveler can become the cause of events they are investigating, or in Robert Heinlein's story By His Bootstraps. It is also seen in the concept of a time traveler giving Beethoven his own music, or a scientist receiving the plans for a time machine from their future self, and then building it, only to send the plans back in time. Physically, the Bootstrap Paradox implies a closed time-like curve, which is mathematically possible in solutions to Einstein's field equations under specific conditions, but its physical plausibility remains uncertain. It is related to the Novikov self-consistency principle, which suggests that time travel could occur only if it does not create paradoxes, allowing self-consistent loops to exist. Ultimately, the Bootstrap Paradox illustrates the logical tensions of time travel within physics and philosophy, showing how the very idea of traveling back in time can defy our understanding of causality and the nature of existence, making it one of the most intriguing paradoxes in discussions about time, identity, and the universe. The cosmological horizon paradox, often called the horizon problem, is a significant puzzle in cosmology that questions why the universe appears so uniform in temperature and structure across regions that should never have been in causal contact due to the limitations imposed by the speed of light. This paradox is most clearly seen in the cosmic microwave background, CMB radiation, the faint glow left over from the Big Bang, which shows nearly identical temperatures across the sky, differing by only 1 part in 100,000. The paradox arises because, according to the standard Big Bang model, the universe has a finite age of about 13.8 billion years, and light travels at a finite speed. This means that there are regions in the universe separated by vast distances that are so far apart that light or any form of information could not have traveled between them since the beginning of the universe. If these regions were never in contact, it is mysterious how they could have reached the same temperature and density, achieving the remarkable uniformity we observe today. For example, 2 regions on opposite sides of the sky are separated by about 28 billion light years, and there hasn't been enough time since the Big Bang for light to travel between them to allow thermal equilibrium. Yet, they exhibit nearly identical temperatures in the CMB. This apparent contradiction between theory and observation is the essence of the cosmological horizon paradox. The resolution to this paradox came with the development of the inflation theory in the early 1980s, proposed by physicists such as Alan Guth. Inflation suggests that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, growing many orders of magnitude in size in an incredibly short time. Before this rapid expansion, the entire universe was small enough for all regions to interact and reach thermal equilibrium. When inflation occurred, these regions were stretched beyond each other's horizons, preserving their uniformity across vast distances. Inflation not only solves the horizon paradox, but also explains the flatness of the universe and the origin of the tiny fluctuations seen in the CMB, which later seeded the formation of galaxies and cosmic structures. The cosmological horizon paradox led to the refinement of cosmological models, revealing the need for inflation and deepening our understanding of the universe's earliest moments, expansion, and the remarkable uniformity of the cosmos we observe today. The Boltzmann Brain paradox is a mind-bending thought experiment in cosmology and thermodynamics, questioning the nature of existence, probability, and entropy in an infinite universe. It originates from Ludwig Boltzmann's 19th century ideas, which suggested that the universe's low entropy state could be explained as a rare fluctuation in a much larger eternal equilibrium system, governed by the laws of thermodynamics. The paradox arises when applying this logic to a universe that lasts forever. In an infinite or extremely long-lived universe, random quantum or thermal fluctuations could spontaneously create self-aware entities, Boltzmann brains out of chaos, complete with false memories and perceptions, even though such events are incredibly improbable. However, given infinite time, the formation of Boltzmann brains would be far more likely than the spontaneous creation of an entire low-entropy universe like the one we inhabit, which requires a much larger and less probable fluctuation. This leads to the paradox. If the laws of physics suggest that Boltzmann brains are statistically more probable than entire structured universes, why do we find ourselves in a vast, ordered cosmos rather than as disembodied brains floating in thermal chaos with fabricated memories? If Boltzmann brains were the typical observers in the universe, it would undermine the reliability of our observations and the scientific method, as our memories and perceptions could not be trusted. The Boltzmann Brain Paradox challenges our understanding of probability and cosmology, pushing scientists to re-examine models of the universe, entropy, and time. It suggests that a cosmological model leading to the dominance of Boltzmann brains is problematic, implying that for a theory of the universe to be acceptable, it must predict that ordinary observers like us are more common than Boltzmann brains. Various proposals have been made to address the paradox. Some suggest that the universe will not last forever, eventually decaying before Boltzmann brains can dominate. Others argue that cosmological models, like those involving inflation, need to be constructed in a way that avoids the conditions under which Boltzmann brains become the norm. The Boltzmann Brain Paradox challenges assumptions about the nature of reality, observation, and the ultimate fate of the universe. It forces us to question whether our structured experiences reflect a genuinely ordered cosmos or are merely fleeting fluctuations in a... Thank you for watching this video. If you enjoyed, please leave a like and subscribe and let me know in the comments if you would like to see more videos like this one. Thanks again. Goodbye.